Hello, everybody. Let me summarize some of the ideas we have studied together in section 2.5 about continuity. So as you can see, the limit of function f of x when x approaches a is exactly the value at a of that function. We call it the function f of x continuous at this point. And some of the remarks are, first, f of a should be defined. Second, the limit of the function when x approaches a should exist. And the third one, limit of that function when x approaches a should be exactly f at a, of x at a. So there are some discontinuities concepts. So the removable discontinuous point is, as you can see, at the point when x is equal to 2. We can remove this discontinuity by defining the value of f of 2 should be this value right here, or infinite discontinuity, as you can see in the second figure, or jumped discontinuities is in the third one. And we will have a definition of left and right discontinuity, continuous continuity here when x approaches a from the right, or x approaches a from the left. So, and here are some basic things about continuous of two functions f and g. The theorems say that the sum or the difference of the two continuous functions will be still continuous, or c times f is continuous if f is continuous, or the product of two continuous at a point would be also continuous, and the quotient of two continuous function is also continuous, provided that g should not be 0 at that point. Remember, when theta approaches 0, cosine will approaches 1, or the limit when theta approaches 0, sine of theta will be 0. And a very special function, tan of x, we see that there are so many vertical asymptotes of tan of x. For example, you can see x is equal to -3 pi over 2 is one vertical asymptote. And another one would be at x is equal to -pi over 2, or x at pi over 2, and so on. This is the graph of the tangent function. Okay, the theorem. All these functions are continuous on their domain. Okay, remember this? The polynomial, trigonometric functions, exponential function, rational function, roots functions, inverse of trig functions, logarithmic functions. And another theorem is that the composite function, if f and g is continuous, when g is continuous as x is equal to, when x approaches a, and f is continuous at g of a, then the limit of the composite function f composite g of x when x approaches a will be f of limit of g of x when x approaches a. And the intermediate value theorem, saying that if f, consider the interval from a to b, f of a is different from f of b, and n is any value between fa and fb, there should have an x between a and b such that f of x and f of c, there's an c in between a and b such that f of c would be n. And here is a summary of the tangent and cotangent and stuff here. We see that tangent, I explained in the class already, is this axis. Whenever you want to find a tangent of an angle alpha, what you need to do is to connect the origin to that angle, and wherever it cut the axis here is the value of the tangent. We see that, for example, at theta is equal to 0, tangent will be the point here when we connect the origin 0, and this, it will cut the axis at this point, we call it at 0. Or the special angle when alpha is for pi over 4. We see that at pi over 4, sine of alpha is equal to cosine of alpha. Therefore, tangent of that angle would be 1, correct. And here, let me do some more example for you so that you have a reference in dealing with the homework. Okay, look at this. Suppose that we are given the function f of x here. We have to explain why this function is discontinuous at a given point A. In this case, the point A is 2. So in order to do this, let us just do as we normally do. We see that at x is equal to 2, f of x is defined, right? It is defined, then we're good. The next steps, we need to find the limit of this guy when x approaches 2, right? X squared minus 2x divided by x squared minus 4. So we need to find the right hand limit and the left hand limit. So let us consider when x approaches 2 from the right hand side. Okay, and we see that the numerator, we can factor it out, right? Here, x is a common factor. So take it out. It will be x times x minus 2. And the denominator, we know that it is x minus plus 2 multiplied x minus 2. C. Here, the numerator, x minus 2, will cancel with the denominator term. And this fraction becomes the limit when x approaches 2 plus of x divided by x plus 2. We see that this function is continuous, the quotient of two continuous functions, right? The polynomial on the numerator is continuous. This denominator is also continuous when x is different from 2, from negative 2. Right, and here it is continuous as 2. So we can simply substitute the value of this to the function. It is 2 divided by 2 plus 2, which is 2 over 4 or 1/2, right? Then we see that from these, okay, one more thing. Let us consider the limit when x approaches 2 from the left. We'll do the similar thing, right? And it is what? The same thing. Similar approach. We will end up with this. And we see that the left-hand limit is equal to the right-hand limit. Therefore, the limit of this should be 1/2, right? And we see that the limit of the function at 2, the function f of x, when x approaches 2 should be 1/2. But the value of the function when f at 2 is defined as 1. So 1/2 is different from 1. Therefore, this is a discontinuous point, removable discontinuous, right? Which one is the correct answer? So f of 2 is defined, that is correct. Limit of this is finite, that is correct, that is 1/2. But they're not, no, they're equal. Oh, they are not, it means that this guy and this guy is not equal. So then this should be a correct answer, right? Very good. Let us move on to another example. Okay, now consider the function f of x when x is e to the x when x is negative, and a polynomial x cubed when x is positive at the point a is equal to 0. Okay, we see that these two functions are continuous on negative infinity to 0, the domain of this, right? And from 0 to infinity, the e to the x is continuous on the first interval. X cubed is also continuous on the second intervals. Therefore, the only point we need to check is at the point x is equal to 0. What we need to do is to check the left hand limit of x when x approaches 0. And when x approaches 0, the function of fx is defined as e to the x, right? E to the x. Therefore, this function is continuous at 0. Therefore, we simply substitute the value to this. It is e to the limit of x when x approaches 0 from the left. It will be e to the 0, or that is 1. That is the left-hand limit. How about the right-hand limit? So when x approaches 0 from the right side, the function f of x takes the value of the cube function here, which is simply 0, because this function is continuous at 0. So what we need to do is to substitute the value of this. And we see that the left hand limit and the right hand limit are not equal to each other. Therefore, the limit does not exist when x approaches 0. Therefore, you can answer this, right? Okay. In the next example, let us see, okay, how would you remove the discontinuity of f? In other words, how would you define f of 5 in order to make f continuous at 5? Okay, first, let us compute the limit when x approaches 5, right? We know that we are not allowed to pick value 5 because it makes the denominator 0, so be careful. With this guy, we can factor the numerator and see. And we know that this quadratic function would be x minus something times x minus something divided by x minus 5. And we know that this guy is negative 5, then we guess this is negative 5. And here would be no, it's not 1. Oh, interesting. Oh, this is number 4. My bad. I copied the wrong number here. Okay, this is 4. Oh, it makes our life easier. Okay, then this one should be number 1. Right. And we see that x, you can file it and see, double check the answer. Okay, x minus 5 cancel with x minus 5. Therefore, this limit becomes limit when x approaches 5 of x minus 1, x plus 1. We see that x plus 1 is a linear function, or the polynomial of degree 1. It is continuous on the whole real lines. Therefore, it is continuous at 5. So the value of this will be simply the substitution of this to this, which gives us number 6. So we see that the function, the limit of this function will approaches 6. It means that we should define f at 5 to be 6 to make it a continuous function. Okay. Move on to another example. Okay, explain why, and using theorems, why this function is continuous at every number in its domain. Okay, we see that first, we need to find the domain of this function. This is a rational function. Therefore, the condition is that the denominator should not be 0. Otherwise, it is not defined, right? But we see that x squared is always positive. Therefore, x squared plus 4 will always be larger than 4. Therefore, the denominator is always different from 0. So, say that it's always true, right? Therefore, this rational function is continuous on R, or the domain of this is from negative infinity to infinity. So from a theorem, we see that the rational function is continuous on its domain. And here, the domain is all real numbers, right? Then, therefore, this one should be the correct answer. Okay? Now, let us move on to another example. Use continuity to evaluate the limit of this guy when x approaches 16. Okay, very interesting. We see that. Now, let us find the domain of this guy and see. What is the condition? or in this case, our conditions. So the radical sign here, it means that the terms under this radical signs should be positive, or say that x should be positive, and 20 plus x should always be positive. Or in this case, x should be larger or equal to negative 20. So here is the real lines, and here is 0, here is 20. So in the first condition, say that, okay, x should be larger or equal to 0, right? And the second condition, x is, negative 20. We should care about negative 20. It is here. Okay, x is should larger or equal to negative 20. So the intersection of this gives us the domain. Will be from 0 to infinity, right? Okay, this is the domain. It is, therefore, this rational function is continuous on 0 to infinity. And this value, where x approaches 16, it is continuous at 16. Therefore, the limit of this is simply the substitution, right? Limit of 20 plus square root of x divided by 20 plus x when x approaches 16. Will be, let us write it clearly. Okay, limit of a quotient will be a quotient of limit. And we see that at this point, we can write it limit of 20 when x approaches 16 plus limit of square root, and then it will be square root of the limit when x approaches 16. And this is the square root of limit when x approaches 16 of 20 plus limit of x when x approaches 16, or limit of a constant will be a constant plus square root of 16, and here square root of 20 plus 16. Simplify it, right? You find the result. Do it yourself. Another example. So we need to compute the limit of this guy. Wow, interesting. You see that, let us call the function f of x is sine of x, right? And the function g of x is x plus sine of x. Therefore, we see that f composite g applied to x would be, let me write it slowly, f of g of x, which is f g of x is x plus sine of x, right? Therefore, f of sine of x, now this guy is the input, then it becomes sine of x plus sine of x here. Interesting. Okay, now you see that the trig function are continuous on its domains, right? Therefore, f and g is continuous on the whole real lines. So we see that limit when x approaches pi of g of x will be limit when x plus sine of x approaches pi becomes, it is continuous on R, therefore it is continuous at x is equal to 5, excuse me. Therefore, we can simply substitute the value to this. It will be pi plus sine of pi. Sine of pi, remember the unit circle is here. This is the sine axis. This is pi. Project to the sine axis, it will be 0. Therefore, this result will be pi plus 0, and which is pi, right? It is pi, and the sine function is continuous at pi, right? So therefore, limit f composite g composite f composite g, sorry, x when x approaches pi will be f of limit when x of g of x when x approaches pi, which is f of pi, f of pi is sine of pi, and sine of pi is again 0.